So when considering the fundamental theorem of gradient vector fields, I just tried to answer the question of what was going on. That we looked at how we could compute a line integral instead of having to go through the long process. Instead, we can be sneaky and use the potential function and just evaluate the endpoints of the line integral at those endpoints of the potential function. Now I'm going to talk about the geometry. So what does that mean geometrically? Let's say that this blue is representing our gradient vector field f. And let's say that we have some path, and we're going to start down here where t equals a, and we're going to end up here where t equals b, and we have a path that travels. And we just found that when I consider this path integral, we'll call this path c1, just for naming's sake. We just decided that this path integral, the amount of work that's done by our vector field f along that path, is going to be our potential function evaluated at c of b minus our potential function evaluated at c of a. But check this out. This is where it gets interesting. Let's say I have a different path. Instead of taking this long squiggly route, let's say that I just took some straight line route, and let's call that path c2. Well, we also know that the line integral over c2 of f is going to be exactly, because it is just a gradient vector field, it didn't matter what the path looked like, I can do the exact same thing. I find that the path integral over this, I should call it a vector line integral, that's what we call it in this class, is going to be the difference of the endpoints evaluated at our potential function. So these two things are exactly the same thing. And that's a really cool, interesting result. And maybe I should write that down as an interesting result. The interesting result is, if f is a gradient vector field, then we will always have the case that the vector line integral of this path and this path will be equal to each other if f is a gradient vector field and we also have to have that c1 of a is equal to c2 of a, meaning they both have to start in the same place, and c1 of b has to be equal to c2 of b. They both have to end in the same place. And it really doesn't matter what path we take. I mean, we could take, I'll use a red marker, and we could have some path that maybe went like in this big loop-de-loop and then all the way around here and then back again. And as long as it starts and stops at the same spot, we know that our line integrals are going to be exactly the same. The final thing, although I did just make this messy, let's look at a special case. A special case in which our path, let's say we have some special path where c of a is exactly equal to c of b. These special paths are called closed paths. And why are they called closed paths? Well, it's because you're starting and stopping in the same spot. So here's an example. This is where c of b is equal to c of a. I have some path. It can go wherever I want, but it has to start and stop at the same spot. So for any closed path, we just decided that our line integral over this closed path is going to be given by the line integral over f ds of our closed path is going to be phi of c of b minus phi of c of a. But if phi of c of b is equal to phi of c of a, then anytime I take a line integral over a closed path, this is going to be exactly equal to 0. And this property, the fact that our line integrals over closed paths are equal to 0, is the property of being a conservative vector field. So this gets to our definition of what it means for a vector field to be conservative. We say that if our line integrals, our vector line integrals over a path c equals 0 for all closed paths, so this c had to be a closed path, on an open connected domain, then f is conservative. There are a few things that I want to point out here. So one is, this is a technical criteria that you couldn't have some crazy gaps and holes going on in your vector field. Because it's possible that maybe you have gaps and holes in your vector field, and so that you would end up with line integrals that were not equal to 0 under those crazy circumstances. So we put these in. It's technical, and I don't really want you to care that much about it. But what I do want you to care about is the fact that in common language, when we're dealing with nice vector fields, a conservative vector field is exactly the same thing as a gradient vector field. The gradient vector fields are conservative. The other thing that I want to point out that's sort of a notational thing is that when C is a closed path, sometimes notationally we indicate that by writing a circle there. So this circle in the center of our integral, when we're representing our vector line integral, the circle says that C is a closed path. So that's something to highlight as well.